my name is Nick Tabin, and this is part 1 for Dr. Osbay's ANSYS Fluent project, the combined Poiseuille-Couette flow. First, we're going to start in Workbench, opening up Fluid Flow Fluent. We're going to go and edit our geometry. So while we had the freedom to choose whatever fluid we wanted, length, height, Reynolds number, as long as it stayed within the top 25, the uppermost 2500 of the Reynolds number, I chose 2400, and then found my length, height, and my mu value accordingly. I chose to do a smaller height for my pipe, and we'll see that it is going to be 0.01 meters or 1 centimeter. So to start, we're going to put ourselves in the 2D plane, starting from our origin, and this is just going to be a basic rectangle with the height I said. So because I chose 1 centimeter as my height, the total length is 1.5 meters. There should be an extra 0 in there, like that. Now we're going to generate a surface from a sketch, choose any point on our line and click generate, and then if we zoom all the way in, it will be grayed out, showing that we now have a 2D surface. So now we're going to go to the mesh. It takes some time to load up. Now, what I'm going to do is change this to an edge find mode, and I'm going to begin creating my named selections. So this top wall is going to end up being the wall that moves at the designated speed. Just X out of that real fast and make sure that we're on the bottom wall. So this is going to be bot wall. This left hand side here is going to be our velocity inlet. And then this back side over here in the bottom right hand corner, it would be easier if I go like this. This right side here will be our P outlet. Now that we've done all this, we're going to actually build a mesh. So, and choose this, apply it, and now instead of quadrilateral dominant, I'm going to elect to use triangles. You can use however you like, but I prefer the triangles, and I'll point out to why later. We're also going to change our element size to 0.0015, and then regenerate that, and it's going to take some time. You see it got super blacked out, and now we have a mesh, but we're going to do one more thing, and that is going to refine the mesh. Apply, generate. And once it has refined it, it's done refining, and as you see, it got a lot smaller, a lot finer of a mesh here. And we have all of our name selections here. So now we're going to go back to Workbench. I'm going to update the project. It's going to begin updating everything downstream, but we're going to go in and actually end up editing the setup and the solution. So that error popped up because I updated the entire project and not just the mesh. You could do either one, but now we're going to go into the setup. I run double precision, and you can do as many solver processes as you like. I'm just going to use 2 for this. So now this is our loaded in mesh with our velocity inlet in blue and our pressure outlet in red, but we do need to go and actually change what type of model it is. So this is going to be a viscous 2D laminar. So we need to make sure we go to model and change that. The next thing we're going to do is under this fluid, or rather under this fluid here, we're going to edit it. So I chose to keep air. But for my specific setup, I used a density of 1.1, and the viscosity, which I found to be 0.0034375. Change create, and then close. And now our boundary conditions. So for this specific one, we were given a free stream velocity of 5 meters per second. So we're going to go into V inlet and change that, and that's been applied. Our outlet, we're going to want to make sure we prevent reverse flow and apply that. And now, what we are going to do is go over to initialize. So initialization method, we're going to do more settings. Number of iterations, I'm going to do 75. Okay. And then our calculation for iterations, I'm going to do 150. So now all of that has been set up. What we can do now is come to run calculation and do initialize and calculate. And so we can see it converged at 26. So now, next step is to get graphics. So we're going to go into contours, we're going to do a new contour. And so we're going to get rid of all of these in here. And for this, I'm going to show the velocity contour velocity. So we're going to just name this velocity. I'm going to hit save and display, close. So now, if we zoom, actually there's one thing I did forget to do, and this simulation I just ran is showing 2 non-moving walls. For what we're actually supposed to do, it's going to be the top wall is going to be moving, and then the bottom wall is going to be stationary. So in order to change that, we're going to go to top wall, want this to be a moving wall, and we want the speed to be 3 meters per second, and we want it absolute. And we do want to make sure that we are under the no slip condition for this. So now, I did forget that. That's the one thing that did need to be done. So we're going to rerun, reinitialize and calculate this simulation. And now we see it's taken a lot longer to actually run the iteration, but it did not. So now if we zoom in here on our velocity and magnitude chart, we see that the bottom blue is an absolute 0, no slip condition is present, and we can see the formation of the boundary layer as it goes along here. The top wall stays in the green at 3 meters per second because, again, the no slip. However, the fluid is sticking to the top wall, and that is moving at 3 meters per second. So now we're going to go down to vectors because we need to overlay a vector chart on here. So in this one, we're going to do the interior surface body vectors. Color by velocity, velocity, yes, all that is correct. Save and display, and it's going to show this. So in order to correctly do this, we're going to redisplay the contour of the velocity contour, and then we're going to add to contours of velocity and magnitude. And now, once I minimize these, make them smaller, we can see how the fluid's moving and the velocity vectors are changing with that. So now zoom back out. So we're going to do the same thing under contours for all of the pressures as well. So we're going to just do static pressure, save and display. We're going to see that's how the static pressure changes. We're going to do another one. It's going to be the total pressure. Again, get rid of all of those. We're going to see how the total pressure changes. And now for final, we're going to do the dynamic pressure. Oh. And again, we see kind of following the velocity profile, or the velocity contour rather, we see a very similar thing happening. So now we have all of our contours and our overlays and velocity. So now what we're going to do is go back to Workbench, go to Results, and edit the results. So now this is how it's going to appear when you load in. So in order to get the velocity profiles at the midline and the end line of this, what we're going to end up doing is going to Location, Line, we're going to call this midline. And so we're going to do it from the 2 points. So the center, the midpoint X is going to be 0.75. It's going to start at 0. Again, 0.75. And this one is now going to be 0.01, which we will see. And we're going to change the samples to 100. Apply. Oh. Why did it go like that? Oh. And there we are. Sorry, I forgot the 0 point. Now we'll see it's dead in the center there. So now we're going to do the same thing. This will be our end line. And so now this one, I'm going to choose a point 1.480 and then 1.48 and 0.01. Again, do 100. And now we're going to get the velocity profile very close to the end there. So actually, I think that's a little far off. So what I'm going to do is 9. Apply that. Now we see it's a little bit closer. So once we've gotten here, next step is we want to make a chart. We're going to call this velocity profiles. So velocity profiles. And then our data series, we're going to do mid, and we're going to change the location to the midline here. We're going to do another series, and this will be our end line. And then location, end line, apply. And so, the next thing we need to do in order to actually make it apply is we need to change the y-axis to be the velocity u, apply, rather, it's the opposite. It's going to be velocity u in the x-axis, and then in y, it's going to be as it approaches, or as it changes in y. There we are. Sorry. And we'll see that the red and the blue lines, so the midline and the end line, are almost a perfect copy of one another, except for this right here, which is more than likely just because of the point I chose. That was very near to the end there. So now we have our velocity profile here. And then just to show more of like what the developing region will look like, I want to put this as developing. And I'm going to choose a point at 0.002 and 0.002, 0.01. Sample is going to be 100. Apply. Then I'm going to go back into my velocity profiles chart, my data series, and I'm going to change this to developing. I'm going to choose that line. We're going to apply it. And now we'll see this is how the velocity profile looks in the developing region, right? So everything is still at 0.01 in the y. It's stuck at 3 meters per second, which is relative to the wall itself, the moving wall on the top. And then this is, as the formation of the boundary layer goes, the velocity profile is changing. And that is it for this project. Then using all of these results we've gathered, then we can move on and find the maximum velocity and the height at which that occurs, either via Blasius or through the data Fluent gives. And then we can determine the pressure gradient out of a report from Fluent. When you export the solution data, there will be a drop down for dpdx, which I will show real quick. So you go to export solution data, change this to this, and then you put a .csv at the end. And if we go down, we will see the dpdx, which is our pressure gradient as it moves along this surface. And that is